A square floor is tiled as partially shown, with a large number of regular hexagonal tiles. The tiles are colored blue or white. Each blue tile is surrounded by 6 white tiles, and each white tile is surrounded by 3 white and 3 blue tiles. Ignoring part tiles, the ratio of the number of blue tiles to the number of white tiles is closest to. So I'm assuming in this question, blue is represented by the shaded one. So this is the blue one. And you can clearly see that each blue tile is surrounded by 6 white tiles. So if this is the blue one, around it are 6 white tiles. 1, 2, 3, 4, 5, 6, like that. And then they also tell you that each white tile is surrounded by 3 white and 3 blue. So for example, this is a white tile. It's surrounded by 3 white, 1, 2, 3, and it's surrounded by 3 blue, 1, 2, 3. So they're saying they don't give us any dimensions of the square floor. They just tell us it's a square. But I guess if you have a pretty decent sized square and you have this kind of pattern, how many blue will you have and how many white will you have? And then they want you to figure out the ratio. So here is a square floor that is tiled in the same way as our diagram up here, but this one is blank. And what we want to do is fill it in, and that will hopefully give us an understanding of the ratio between the number of blue tiles to the number of white tiles. So let's fill in one such blue tile. Let's choose that one. Is it surrounded by 6 white tiles? And currently it is, because everything's white. But let's keep going here. How about the next one over? It will also be surrounded by 6 white. But now I want to color in one below like that. And the reason is this will allow me to see if the white tile is surrounded by 3 white and 3 blue. So if this is the white tile that I'm looking at, is it surrounded by 3 blue? And it looks like it is. And is it surrounded by 3 white? And it looks like it is. So this type of a pattern will fit our conditions of the question. And if you keep circling or shading in blue to meet the requirements as we have, we should get a pretty good understanding of the ratio between white and blue. So after completing the coloring, let's count how many we have. So this row looks like 6 blue, 5, 6, 5, 6, and 5. So this looks like 11 times 3, 33 blue. And then how about the white tiles? How many are those? I'll label them down here. This row looks like 6, 6, and they look like pretty much 6 in every single column here. So how many columns do we have in our diagram? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 times 6, 66 white. So this is an approximate ratio between the blue and the white based on our diagram, and it should hold true for any square floor regardless of the dimension. And this gives us, if you reduce it, 1 over 2. And therefore the answer to number 25 is E. A triangle can be formed having side lengths 4, 5, and 8. It is impossible, however, to construct a triangle with side lengths 4, 5, and 9. Ron has 8 sticks, each having an integer length. He observes that he cannot form a triangle using any of these sticks as side lengths. The shortest possible length of the longest of the 8 sticks is. All right. So they are saying that you've got sticks that are 4, 5, and 8, and you're able to form a triangle like that. So this is 4, this is 5, and this is 8. But what if you have 4, 5, and 9? So you have 4, you have 5, and then you've got 9. Well, you can't form a triangle with sticks that are identical in length. This is 4, this orange one was 5, and then this red one was 9. You see how it's impossible to form a triangle with sticks that are the same length? So there's a rule, right? If you have a triangle that's got 3 sides, A, B, C, A plus B has to be greater than C, right? So for example, in this triangle right here, we had 4 plus 5, and that's greater than 8, correct? In this triangle, or it's not a triangle, in this scenario, 4 plus 5 was equal to 9. And because it's equal, it cannot be made into a triangle. The sides can't be constructed in a way to form a triangle. So this is the fundamental relationship or rule. And if A plus B is equal to C, this means triangle not possible. All right? So that is basically what we have to work with. So they're saying you've got how many? 8 sticks. 8 sticks. 1, 2, 3, 4, 5, 6, 7, 8. And none of them can be used to form a triangle. And they want you to figure out the length of the longest of the 8 sticks. All right, let's try to squeeze in everything instead of going back and forth. All right, so the longest, I'll let this one be the longest. They're going to be in increasing order. So we want the shortest possible length of the longest stick. So again, we want shortest, so these kinds of questions, shortest, longest, we have extreme case scenarios. So I'm going to start with the shortest possible first stick, a length of 1. Because they tell you that they have integer lengths, and that's the smallest integer. How about the next one? The next one, I want it as small as possible, so I'll make it 1. Now you say, okay, well, make them all 1. That'll make the last one 1. But if you make them all 1, you'll be able to form triangles, right? Because if you have 1, 1, and 1, like that, you can make a triangle. It'll be an equilateral triangle. We want a scenario where we can't make a triangle. That's what the question says. He cannot form a triangle using any of these 3 sticks. So the first 2 are okay. But the third one, we will use this scenario. A plus B equals C. If you do that, you can't make a triangle. So if this was A and this is B, C will be equal to 2, right? Because with these 3 numbers, 1, 1, and 2, it's impossible to make a triangle. And we explained that a little bit earlier. So let's just keep going using that rule right there. So the next one, we will have to make it as the sum of the previous 2. So 1 plus 2 is 3. If you do that, then these 3 numbers cannot be used to form a triangle in terms of the lengths of the sides. Keep going exactly the same way. 2 plus 3 is 5. Therefore, sticks of lengths 2, 3, and 5 cannot be used to make a triangle. And then 3 plus 5 is 8. 5 plus 8 is 13, and 13 plus 8 is 21. So using this formula, we got 21 as the length of the 8th stick, and that's the shortest possible. So the answer to number 25 is B. And this sequence has a special name. It is called a Fibonacci sequence. So if you are interested, you can read more about this special type of sequence online. Each of the integers 226 and 318 have the digits whose product is 24. How many 3-digit positive integers have digits whose product is 24? So we've got a 3-digit number, say A, B, and C. And if you take the individual digits and multiply them by each other, they will equal 24. And they want you to figure out how many such numbers are there. Well, 24, that number itself, we want to break it down to its prime factors. So it's 2 times 2 times 2 times 3. So its prime factors are 1. 1 goes into it, of course. But 1 is not a prime factor, but it is a factor. 2, 3, 4, 6, 8, 12, and 24. These are the numbers that divide into 24. But we only are interested in the single digits because that's how we're going to make this number. We can't put a 12 or a 24 in there because those are obviously double digits. So our numbers are going to consist of some of these numbers. We don't know yet, but the criteria is that those three numbers, when multiplied together, have to equal 24. So let's start making a list here. So if I choose 1, let's start with 1. Can I choose 2 as the next digit? If I did, 1 times 2 times something would have to equal 24, and that something would be 12. And that's obviously not going to make a 3-digit number. So I can't choose 2, but I can choose 3. Because 1 times 3 times some number equals 24, and that some number is 8. So there you go. I've got my first number of all the numbers I need to find. So let's keep going here. 183 would also work, right? I just reversed the order a little bit. And I will stay with these numbers and just try to find more combinations of them. I'll stay with 1, 3, and 8. So 3, 1, 8, 3, 8, 1, 8, 1, 3, and 8, 3, 1. All right, so all of these have this property that when you multiply the digits together, it equals 24. So now let's move on. We've exhausted all the ones. Or have we? Aha. Let's keep with 1 then. If we haven't exhausted it, let's keep with 1. I can't choose 2. I've already explained why. I've already done the 3, so now let's go with the 4. 1 times 4 times some number is 24, so that number has to be 6. Okay? So now these 3 digits, I will try to make more numbers out of. 164, 416, 461, 614, and 641. All right, all of these have that property that when you multiply the digits together, it equals 24. Okay, let's move on. Can we go with 1 again? 1, 6. If I move to the next one, therefore this would have to be 4. 1, 6, 4. But I've already done that. See, I've already exhausted this. So this one would be essentially a repeat. So that's no good. How about 1 and 8? And therefore this would have to be 3. But I've already done that over here. So I have indeed now finally exhausted the ones. So let's move on. Let's move on to 2. Just 2 by itself. Then if I put the next digit as 1, that's not going to work, right? Because then this would have to be a 12. So that's no good. How about if I put the next digit as a 3? 2 times 3 is 6. And then 6 times what is equal to 24? 4. So there you go. That's another combination. And then with these 3 numbers, I will create more numbers. So 2, 4, 3, 3, 2, 4, 3, 4, 2, 4, 2, 3, and 4, 3, 2. All right, so I hope you're following that. So let's see, I did 2, I did 3, I did 4. What's next? If I have 2, stay with the 2, I guess, and let's put the next one over, which is 6. If I have 2 and 6, that 2 times 6 is equal to 12. So 12 times something has to equal 24, and that's 2. Nothing in the question says that I'm not allowed to use the same number twice. So 262 it meets that criteria. Now can I get more combinations? 2, 2, 6. And 622. That would mean just a little bit of a order reversal. And at this point, let's see if I can keep going. 2, 8. 2 times 8 is 16, but 16 times nothing is 24, so that's no good. And then if you keep going like this, you'll find that we have pretty much exhausted all the combinations, because if you start with 3 and then you keep going, you'll either find that there's no way you can do it, or you will keep coming back to the ones that we just did. So I encourage you to sit down and work through this problem. So how many did we find here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 numbers that have that criteria where the digits, if multiplied, equal 24. So number 25, the answer is E. The digits 1, 2, 3, 4, and 5 are placed in one of the boxes so that the resulting product is correct. If each of the 6 digits is used exactly once, the digit represented by the question mark is. So again, this is another trial and error question. Is there a systematic way in terms of like a mathematical formula, And perhaps, but the truth is that describing it in that way is actually more confusing than trial and error. And more time, not just confusing, but more time consuming. Confusing and time consuming. So I'm just going to show you trial and error. And I really believe that this is the best way to do it on a math contest. So what I'm going to do is I'm only going to concentrate on the top 2 numbers. Okay? And very quickly you can make a list of the top 2 numbers. 1, 2, 1, 3, 1, 4, 1, 5, like this. You understand? 1, 6, like that. And very quickly I can do that for all of these, so I'll just write it all out. So these are the possible numbers that could be up here, a 2-digit number. And now, of course, we're multiplying by a 3rd digit. So we'll just trial and error this. All right. So here we go. Now, if that question mark, I'll put it up here. Let's say it's a 1. We'll start with 1. Then that means that we can't use any of these guys, right? Because we can only use each digit once. So we also can't use anything that has a 1. So all this is out. All right? So we can only use the remaining 2-digit numbers. But if you do multiply 1 by any of those, it's the exact same thing. You don't get a 3-digit number. So in a very quick way, 1 is not possible as the question mark digit. So that's great. We can now move on to 2. So let's say the question mark digit is 2. Well, then we have to eliminate these guys because you can't use them because they have 2's in them, and each digit can only be used once. And similarly, I've got to take out any number that has a 2 in it, so all these guys. All right, these guys are all gone. Now we proceed with what's left. 2 times any of these have to give a 3-digit number, and that's not going to be possible for a lot of these. The only time you'll get a 3-digit number, I think, is when you get up to 51. Yeah, because 2 times 46 is 92, right? So let's see. 2 times 51 is 102. 2 times 53 is 106. 108. 112. 122. 126. 128. And 130. So very quickly we did that. Now the criteria is that the 3-digit number has to contain the other 3 digits that we had not used yet. And 0 is not one of the digits at all. So that's no good, that's no good, that's no good, and that's no good. And no digit can be used more than once, so that's no good, that's no good. All right, let's see this guy here, 126. How did we get 126? It was 2 times 63, correct? And that is 126. No good because the 2 is being used more than once. And then 128 is obviously no good because there's an 8 in there. So 2 cannot be the question mark. All right, so you see how the trial and error. So let's hope that the next one we can get it, which would be a 3 as the question mark. So here we go. Let's try 3. If 3 is indeed the question mark digit, we have to eliminate these guys because they have 3's in them, and we also have to eliminate anything that has a 3. So these are gone and these are gone. All right, let's go ahead with this. Similarly, if you multiply 3 by any of these 2-digit numbers, it must produce a 3-digit number because that's the criteria. And I think that only happens when you get over to this side here, 41, because 26 times 3 is 78, right? All right, so 41 times 3 is 123. I'll just do these here. 42 times 3, 126, 135, 1. So there you go. I multiplied them all by 3 to see what we can get. All right, so 41 times 3, this guy right here, times 3, is 123. Is that good? Well, no, because we've already used 1 and 3, and that product has a 1 and 3. Because remember, all these digits can only be used once. So, no good. 126, same thing. There's a 2 there. That's not going to be good. 135, no, because it's got a 3 in it. 138, well, it has an 8, and 8 is not even part of our criteria or selection. How about 153? Well, no, because there's 2 5s. How about 156? Again, 2 5s. How about 162? Well, let's see. We have 54 as our 2-digit number. Our question mark is 3. And then that gives 162. I believe we have it. Each of these digits is only being placed once. 1, 2, 3, 4, 5, 6. There you go. We got it. And therefore, the question mark digit is 3. So as you can see, without too much pain, we got this answer correct with trial and error. So number 25, answer is B, which is 3. A grid with 10 rows and some number of columns is made up of unit squares as shown. A domino can be placed horizontally or vertically to exactly cover 2 unit squares. There are 2,004 positions in which the domino could be placed. The number of columns in the grid is. So we have a domino, and that domino is going to be placed on this grid. And initially, let's try looking at what happens when you put domino in the rows. So you're putting the domino like this. So initially in this direction. And we can probably do it like that, right? That's the first one, like that, and then so on. We're going in a horizontal fashion. So let's make a little table. We've got row number 1, correct? How many ways can I put the domino? Well, it would definitely help you if we knew the number of columns. We don't know the number of columns. That's what we actually have to figure out. But let's just say the number is n. Okay? Well, if you have n, then the dominoes can be placed there, 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 like that, and so on. How many ways can that be done? N minus 1. Now, if you say, well, I'm not convinced of that, no problem. Just make a little, like I always do, just make a little miniature diagram for yourself and figure it out. So let's say I make a little miniature diagram for myself just to see what it could be like. And in this one I chose 1, 2, 3, 4, 5, 6, 7, 8. 8 as my n. Well, how many times can I place that domino? 1, correct? 2, and then 3, and then 4, and then 5, 6, and 7. 7 times I could place that domino if there was 8 columns. You see how I got n minus 1? All right, so let's move forward here. Row 2, same thing. We can place it in n minus 1 ways, the domino, and so on. Now the good news is we know the number of rows. It's 10. So that means for each of these 10 rows, the number of ways we can place the domino is n minus 1. So the total is n minus 1 times 10 rows. All right, so that takes care of the horizontal. Now let's turn our attention to the vertical. And what I mean by that is basically I'm going to now put the domino in this direction. So 1, 2, 3, like that, and 4, and so on. Well, because there's 10, I can easily figure out how many times it goes. It goes 9 times. So let's make a very similar table. So in the first column, how many times can I place that domino? I could do it in 9 ways. In the second column, in how many ways can I place the domino? Another 9. And in the third column, another 9, and you get the point, right? Dot, 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 and so on. Well, what's the total? Well, there's n columns, and for each column, there's 9 ways of placing the domino. So n times 9. And there you go. Now we have to add up these. These are the number of ways that you can place the domino horizontally. And this represents the number of ways you can place the domino vertically. So 10 times n minus 1 plus 9n is equal to, they give you the total, 2004. And now you just solve for this. So 10n minus 10 plus 9n is equal to 2004. So that means you got 19n is equal to 2004 plus 10. So that's 2014. And therefore n is equal to 2014 divided by 19, which is 106. And since n represented the number of columns, this diagram has 106 columns. So number 25, the answer is B. How many different combinations of pennies, nickels, dimes, and quarters use 48 coins to total $1? All right, let's first make a little table for ourselves, and let's see what we get. Pennies, nickels, dimes, quarters. Now, we are not told much in this question. We don't know if we have to use a penny, nickel, dime, and quarter for all the combinations, or can I not have one of those coins? You know what I mean? Like, can I have 0 nickels and 0 dimes? Well, we'll just go with this. So the number of coins has to be 48, right? So if I have 48 pennies, I'm just going to start in that point, at that point. If I have 48 pennies, they're all pennies, I've got 48 cents. So I'm going to put my amount here. Now, obviously, that's no good, right? Because I've got a total of $1. So no good there. But that's okay, because I need a starting point. One thing I immediately noticed, though, is that when I choose the number of pennies, I've got to choose a value that makes me get a number that's divisible by 5, because that's the only way I can get the remainder to add up using nickels, dimes, and quarters, because nickels are 5s, dimes are 10s, and quarters are 25s. So 45, let's see what happens. If I have 45 pennies, how many coins are remaining? that's how I'm going to do this. Well, 48 coins is what we have to use. I've already used 45 of them as pennies, so 3 coins are remaining. Okay? Now, I've got to make a buck with 3 coins and 45 pennies. All right, well, what was my amount for 45 pennies? It was 45 cents. All right. But I want to know how much more I need. I've got to use the 3 coins to get 55 cents. So amount needed. All right. So for this one, it was basically 52 cents, but there was no way of us getting it because we've already used up all the coins. So that was a dud. But how about, can I get 55 cents using 3 coins? I think so. Let's see here. If I use 2 quarters, that'll be 50 cents, and then 1 nickel. That'll do it. And there's 0 dimes. So I think this one is one possibility. I'm sure of it. And also, I'm also sure that in our combinations, it's allowed that you don't have to use all the coins. What I mean by that is that you don't have to have at least 1 penny, 1 nickel, 1 dime, 1 quarter, because in this scenario, as you notice, I have 0 dimes. All right, let's keep going here. We got 1 so far, but obviously the answer choices, they've got quite a few more. All right, let's go down to 40 pennies. If I've got 40 pennies, that's 40 cents. Amount needed would be 60. I've got 60 cents more that I've got to create. Now, how many coins do I have remaining? 8. With 8 coins, can I get 60 cents? Okay, I'm pretty sure I can. How about if I have 1 quarter, that'll be 35, and I've got 7 nickels. That'll do it. And then 0 for dimes. Any other way? How about if I have 0 quarters, 4 dimes, and then 4 nickels? That will do it also. All right, I've got 2 there. Good. Making a little bit of progress. And then let's go down to the next one, 35 pennies. 35 pennies, that's 35 cents. And then that means I've got 65 cents that I need to create with how many coins? 13 coins. All right, let's see. How can I do this? 65 cents. I think the only way is with 13 nickels. Yeah, 0, 0. Because if I start using quarters, I won't be able to match this 13 coin criteria or requirement. You can get 65 cents with quarters, and like 2 quarters is 50 cents, and then 3 dimes or 3 nickels, would bring it up to 65, but that falls short of 13 coins. So I think this is the only way. All right, let's keep going here. 30 pennies. All right, I've got 70 cents I've got to create, and I've got 18. Oh boy, 18. If all of them were nickels, that would be 90 cents. So there's no way of this working. And then in a very similar way, if I go down to 25, there's no way, because this will be way too many coins. So I think that's it. How many did I get? I got 4. So number 25, the answer is B. 5 students wrote a quiz with a maximum score of 50. The scores of 4 of the students were 42, 43, 46, and 49. The score of the 5th student was N. The average or mean of the 5 students' scores was the same as the median of the 5 students' scores. The number of values of N which are possible is. So our values for the scores are N, 42, 43, 46, and 49. So our average, or mean rather, either one, is going to be N plus 42 plus 43 plus 46 plus 49, all divided by 5. Okay? And this is N plus 180 over 5, which is basically N over 5 plus 36. And this is our mean, average or mean, whichever word you prefer using. Now, we have to figure out what can n be to make the median also n. So what I do is make a little table. And let's see what we get. So I got a little table here. I'm going to have n, median, and mean. And hopefully we won't have to do too many. So we got n here, mean and median. All right, we got to start somewhere, right? So let's start with 1. Well, 1 is important, well, whatever you want to do, but I like it because it shows you that if you put 1 in, you would get a fractional answer for mean. And therefore, there's no way that can work because the median has to be a number, correct? And therefore, since the median and the mean have to be equal, the mean has to be a number. So we can only put numbers for n that are multiples of 5. That's the only way you're going to get an integer value for mean and therefore be able to match the median. All right, so let's start with 5. If n is 5, the mean is quickly calculated as 37. And if n is 37, then what's the median? Well, the median is 43. Does this work? No, because remember, our goal is to make the median equal to the mean. All right, so no problem. Keep going. How about if I make the value of n equal to 30? And really my goal is try to make these means equal to each of these. And that will help me figure out this very quickly. And I guess the quicker way of doing that instead of concentrating on n is just put in the mean values, 42 for example, like that. And if you do that, you'll be able to figure out n pretty quickly. If the mean is 42, and that is equal to n over 5 plus 36, you just 42 minus 36, which is 6, and then times 5 is n. And that would mean n is 30. If n is 30, then what is the median? Well, the median is 43. You see how I got that? Now, is the mean equal to the median? No, so that doesn't work. All right. Not a problem. Keep going. Now let's try the next one, 43. If the mean is 43, you can quickly calculate n. 43 minus 36 is 7. 7 times 5 is 35. So we got 35. Now if 35 is the value for n, what is the median of these 5 numbers? 43. And there you go. You just got a value for n for which the mean equals the median. Great. Now we have to see how many more can we get. All right. Let's keep going here. 46 for the median, or sorry, the mean. If you have 46, put 46 here. 46 minus 36 is 10. 10 times 5 is 50. All right. So if 50 is n, I'll put 50 over here now. What is the median? Median is 46. Does the mean and median equal each other? Sure. All right, we got 2. Now the n can never be greater than 50 because the maximum score is 50. All right, so do we just say, okay, we got 2 values for n, circle E and then end the contest? No, please do not do that mistake. We've got to look at other possible values. Now the good news is that you don't have to go through 49, 48, 47, 46 for n. Why? Because remember, we talked about this earlier. In order for this to work, n has to be a multiple of 5. That's the only way we're going to get an integer value for mean. And because the mean has to equal the median, and the median must be an integer, right? It's just going to be the middle value of a set of integers. Then, therefore, considering all of that, n has to be just a multiple of 5. So we only need to look at multiples of 5. So I'll look at 45, I'll look at 40, and I think that should be it. Because, what the heck, we can, any other multiples of 5? 50, 45, 40, 35, 30. Oh yeah, below 30, so 25, but that's certainly not going to give us a proper answer. Okay, let's work with this. So n is 45, right? So let's do that. 45 for n. So 45 divided by 5 is 9. 9 plus 36 is 45. So therefore the mean is 45. Okay. And then what's the median if the value for n is 45? Well, the median is 45 also. Great. Look at that. See what I mean? By plugging in more values, you get another answer. I've got another value for n for which the mean is equal to the median. Let's keep going here. We'll probably only have to do a couple more, and we should be done with this question. So now let's try 40 for n. If n is 40, 40 divided by 5 is 8. 8 plus 36 is 44. So that means my mean is 44. If n is 40, what's my median? It'll be 43. Okay, that doesn't work. All right, I think that should be it. But let's just try 25, just to be thorough. It's certainly not going to be a correct answer choice, but let's just see. If it's 25, we've got 25 divided by 5, which is 5. 5 plus 36 is 41. So that means my mean is 41. 41 goes here, and therefore my median is 43. So there you go. And I hope I have shown you the right way of doing this. Please don't circle, 2 and move on. Exhaust the question and get all 3 values of n. And those values are right here. So the answer for number 25 is 3, and that is choice A. The Canadian Mathematics Competition reception desk has a tray in which to stack letters as they arrive, starting at 12. The following process repeats every 5 minutes. Step 1. 3 letters arrive at the reception desk and are stacked on top of the letters already in the stack. The first of the 3 is placed on the stack first, and the second letter next, and the third letter on top. Step 2. The top 2 letters in the stack are removed. This process repeats until 36 letters have arrived and the top 2 letters have been immediately removed. Once all 36 letters have arrived and the top 2 letters have been immediately removed, no more letters arrive and the top 2 letters in the stack continue to be removed every 5 minutes until all 36 letters have been removed. At what time was the 13th letter to arrive removed? So we have to make a little bit of a list, a table. So I'm going to start at 12 noon, and every 5 minutes after that, I am going to obviously add some papers. So we got 12, 12:05, 12:10, 12:15, and so on. So here we go. Let's start filling in this table. At 12, the first 3 papers arrive, so I'll just label them 1, 2, and 3. And then after they arrive, they remove the top 2, correct? So when they remove the top 2, I'll just circle those. And then we get to the next time period, which is 12:05. When that time period starts, the only thing that's left in the stack is the paper that I have labeled 1, because papers that were labeled 2 and 3 were removed. Now we add the next 3, and I'll call those 4, 5, and 6. Okay? Now we get to the next 5-minute period. And when you do, it starts with just 1 and 4. Why? Because 6 and 5 were removed. And this process continues. So I'll just do a few more, and then I'll fill in the rest, because you'll get the idea by then. Now at this point, at the 10-minute point, we add the next 3, which are 7, 8, and 9. And then when we get to 15, 2 of those have been removed. So we start off with just 1, 4, and 7. The pages that are labeled 1, 4, and 7. The first one, the fourth one, and the 7th one. Now at 15 minutes, you add the next 3, which are 10, 11, and 12. And then you move to the next time period. But before you do, you have to remove 2. So you start this next time period with the pages that are labeled 1, 4, 7, and 10. Now you add the next 3, which would be 13, 14, and 15. But then you immediately remove 2 of them. And then you start the next time period with 1, 4, 7, 10, 13. You add the next 3, which are 16, 17, and 18. But then you immediately remove the top 2. And you start the next time period with 1, 4, 7, 10, 13, 16. And you add the next 3, which would be 19, 20, 21. And then you immediately remove the top 2. Then you start the next with 1, 4, 7, 10, 13, 16, 19. You add the next 3, which would be 22, 23, 24. And you immediately remove the top 2. And you start the next time period with 1, 4, 7, 10, 13, 16, 19, and 22. Correct? And then, of course, you add the next 3, which are 25, 26, 27. And you go on from there. So at this point, I think you get the hang of it. I think you can do the last few. I'll just fill them in. So I filled it in until all 36 have been added. Now, what I want to do is, now that all 36 have been added, we have to now start talking about what's going to happen next. No more new papers are coming in. Now it's just going to be a clearinghouse. We're just getting rid of them 2 at a time. So I will shift this over and extend this table, and let's see what we get. So at the 55-minute mark, that is when we placed the last of the letters, which were 34, 35, 36, correct? And immediately we removed the top 2. So when we get to the 60-minute mark, these are the only letters that are remaining. And there's 12 of them. So there's 12 letters remaining. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then each of these intervals, you're going to remove 2 until there's none left. So they want you to figure out, when was this guy removed? The 13th letter. Okay, let's see. So in this interval right here, the 60-minute mark, you remove 34 and 31. And if you do, what's left are these guys, 19, 22, 25, 28. At the 65-minute time of this question, we remove the next 2, which are 25 and 28. So now you're left with these guys. Then at 70 minutes, you remove the next 2, which would be the 22nd and the 19th. So you're left with these guys. And then at the 75th minute, you remove the 16th and the 13th letter. And that is what they're asking. At what time was the 13th letter removed? It was removed at 75 minutes from the start, which was 12. 75 minutes from 12 is 1:15. So therefore, number 25, the answer is 8. The sum of all the digits of the integers from 98 to 101 is 9 plus 8 plus 9, 9, 1, 0, 0, 1, 0, 1, which is 38. The sum of all the digits of the integers from 1 to 2008 is So we've got a lot of work to do in this question, but let's take it one step at a time, systematically. First, let's just look at 1 to 10. That's going to be 1, 2, 3, all the way up until 9, right? And if you do that, if you add them up, it's just 9 times 10 divided by 2, which is 45. All right? So that's the first one. Now let's look at 10 to 11. It's 10, 11, 12, all the way up until 19, right? Now we're adding, not the numbers, we're adding the digits. Okay, so be careful. First, let's just add up the units digits. That's just 1 to 9. 1 to 9 is always 45. Then you're adding up the tens digits, which in this case are all ones. 1, 1, 1, 1, like that. And how many of them are there? Well, there's 10 of them. So that will be 45 plus 10. Okay? Similarly, if you go from, this was 10 to 19, if you go from 20 to 29, let's see what the pattern is. It'll be 20, 21, 22, all the way up until 29. Again, if you look at just the units digits, that will add up to 45. And if you look at the tens digits, those are all 2's, and there's 10 of them, so it would be 2 times 10, which is 20. Okay? And very similar, you can keep going until we get to 90, 90 to 99. That's going to be 90, 91, 92, all the way until 99. If you add up the ones digits, it's 45. If you add up the tens digits, it'll be 10 times 9, which is 90. So these guys, if you add them all up, how many 45s do we have? Well, we have 9 of them. So 9 times 45. And then 10 plus 20 plus all the way up until 90 is really just 10 times 45. Because if you factor out a 10, it's like 1 plus 2 plus 3 all the way up until 9. And therefore this is going to be 855. All right, so that takes care of that one. Now we get to the next part, which is going to be hundreds. So let's look at 100 to 109. So we got 100, we have 101, 102, all the way until 109. And then if you're adding up the digits, the units digits will give you 45, the tens digits give you nothing, and then the hundreds digits, there's all ones, so and there's 10 of those, so you got 10. Okay? And then we got 110 to 119. 110, 111, 112, all the way until 119. Units digits, again, give me 45. But now the tens digits give me all ones. So if I add up those, there'll be 10 of those. And then the hundreds digits are, again, just ones. So that just gives me 10. And then similarly for 120 to 129, this gives me 45 for the units digits. It gives me 20 this time for the tens digits because it's all 2's and there's 10 of them, so 2 times 10 is 20. And then for the hundreds digit, it's still 10. And then ... I'll just jump to the 190s. 190 to 199. Units digits 45. Tens digits give me 90. And the hundreds digits give me 10. So adding up all of these, I'm going to have how many 45s? Well, it looks like I'm going to have 10 of those. So 10 times 45. And then these guys in the middle, it's like adding 1 plus 2 plus 3 all the way till 9, but you have to multiply that by 10. So it's 10 times 45. And then these guys, that's pretty easy. That's just 10 times 10. So that's 10 times 10 like that. And if you add up these, that becomes 1,000. All right, so I hope you're getting the hang of this. And we continue like this, and I'll let you do, I'm obviously not going to do every single one from all the way up until 2008. So I'll just tell you what the results are. If you do 200s, right, the 200s, 2 to 299, exactly the way I did for the hundreds here, you'll get a sum of 1100. Okay, No different. It'll be the same pattern, the same kind of style. Nothing changes. If I do the 300s, I will get a sum of 1200. All right? And so on and so forth. So if I do, I'll just write them side by side. 400s, and I add up all the digits, it'll be 1300, and then and so on. Now at this point, we have finished with the 900s, and we are now moving into the 1000 plus numbers. But there is a fortunate shortcut to doing that, and I will explain as follows. If you look at this range right here, that was from 1 to 99, right? So once you pass 1000 and you get to the range 1000 to 1099, all the digits, when you add them together, will be exactly the same. The only difference is that the numbers all will have a 1 before them. So it essentially is the same summation, which in this case was 900, but then you have to consider the fact that every number has a 1 in the 1000th column, and there's 100 of them. So those 100 ones, which total 100, have to be added. So when you're adding the digits from 1000 to 1099, it will equal 1000. Okay? And similarly, we can do the same thing for 1100 to 1199 by looking at 100 to 199. That summation was 1000, but remember, each of these guys will have a 1 in front of it. So since there's 100 of them, there'll be 100 ones that you have to take into consideration. So you take this 1000 and you add to it all of those ones. And if you do, you get 1100. Okay? So that definitely helps us figure all of these out very quickly. So instead of having to go through this painful thing all over again, we can just do this very quickly by adding 100. So the 1200s, these were the 1100s. The 1200s, well, let's look at the 200s. The 200s gave us a sum of 1100. So we have to add 100 to that. So the 1200s would give us a sum of 1200. If you want the 1300s, we would look at the 300s, which is right here, and the 300s had a sum of 1200. And again, when you're looking at the 1300s, you're looking at the same numbers, but each number will have an additional 1. So you have to take into consideration that there's 100 ones. So you add 100 to this number. So that becomes 1300. And similarly, you just fill out the table like that. All right, so we're almost done. Our final is going to be 2000 to 2008, right? So I think I can squeeze that in here. So that's going to be 1 plus 2 all the way to 8, and that is 8 times 9 divided by 2, which is 36. And then I've got to add these 2's, and there's 8 of those, or 9 of those. So 9 times 2, which is 18. And that gives me 54. There we go. I've got all my numbers here. So let's add all these up now. I've got 45. I've got 855, 1,000. Then I've got all of these. I've got 1,000, 1,100, all of these, and finally my 54. Adding up all of those numbers, you get a grand total of 28,054. And for this question, that is answer choice E. Kira can draw a connected path from M to N by drawing arrows along only the diagonals of 9 squares shown. One such possible path is shown. A path cannot pass through the interior of the same square twice. In total, how many different paths can she draw from N to N? M to N. Now the answer choices go up to 9, so that's why I drew all of these. One they've already given us right here, so that's a gimme. So let's see how many more we can get. Well, based on the one that they gave me, I'm going to just draw the exact reflection, which would be like this right here. Right? That's pretty much the exact reflection. Now it's very important for us to denote the direction that these arrows are going, because it might get a little confusing. In addition to that, what I'm going to do is also write a number indicating where I'm going, because this otherwise becomes very confusing very quickly. So this was 1, 2, 3, 4, 5, like that. And they're drawing arrows, so they kind of did that already. So far we have 2, right? So far you can understand how we're going to approach this. The next one is the most straightforward one, which is all the way across. So like this. Sorry, these diagrams are not perfectly drawn, but you get the point. So obviously we're going in this direction. And I want to label it. Not that it's that confusing for this one, but for the next ones it'll be. So far we have 3. Okay, let's see how many more we can get. They have 9 as the maximum. Okay, let's see. Okay, so the first 3 are pretty straightforward. Let's see which direction I can go. How about this way, then this way, and then at this point I obviously don't want to go all the way till n, which is right here, because that would be the same as before. So I've got to do some sort of a creative route here. So I will, like that. And then from here, I'll go here. And then I'll go back up here. And then I can go back there. And then finally go to n. So let's label these in terms of the numbers. So this was 1, then 2, then 3, then 4, 5, 6, 7, 8, and then 9. Okay? So let's go back and keep going like this, see how many more we can get. So let's do the reflection of this. Instead of going in completely random directions, let's do the exact reflection of what I just drew. And that would be like this, and then we're going to go this way now for 3, 4, and then 5, and then 6, 7, 8, and then finally 9. So let's show that this was indeed a reflection. 1, 2, 3, then 4, 5, 6, 7, 8, 9. Alright, so we got 5. 5 is one of the answer choices, so let's keep going here. I have a feeling that it's going to be either 5, 7, or 9, because each of these has a reflection. So I'm going to cross out those. I'm pretty sure that each has a reflection, so therefore it's got to be 5, 7, or 9. Alright, so now where do I go next? I can go this way. And I can go this way. So that will be 2. And then therefore this will be 3. And then 4, 5, and then 6, 7, 8, and then 9 back here. So let's label that one. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And the next one, we'll do the same, but a reflection of what I just did. So instead of going up, we'll go down and like that, across like that. And then down there, and then back down in the same way. And then of course, then we're going to go across here, and then up, and then down, and then finally back to the end point. So let's label this guy. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So far we have 1, 2, 3, 4, 5, 6, 7. So that is gone. So now we're down to either 7 or 9, and this is what separates the perfect scores from the 144s or the 142s. So let's see, can we get any more? Yes or no? And if we do, we're definitely going to have 2 more. Otherwise, we have an answer of 7. And yes, there are more. So it's going to originally start off looking a lot like this guy right here. This one. Right here. It looks a lot like that, right? It starts off in the same way. 1, 2, 3, 4. But if you notice, in that one we came down, right? We came down here, but we're not going to do that. We are going to go across. And that will give us another path like this. And then we come back up like that. So this gives us 1, 2, 3, 4, 5, 6, 7, 8, 9. And as always, there's going to be a reflection of that same path. And that reflection is as follows. This way, this way, this way. And then going across. And at this point, it looks very similar to this guy right here. But instead of going down, we go across like that. And then back down, back across, and then go up all the way to there. So this, let's label it 1, 2, 3, 4, 5, 6, 7, 8, 9. So as you can see, they are all distinct. This is obviously different from that. This is straight across. And if you look at the numbering, they are all different. Here, my second move is in the middle, and my third move is here, my third move is there. So these two are definitely different. These ones, my second move is here, my second move is here. But the fifth move was in the middle. Here, the fifth move is on the side. The last two, the second move is here, the second move is here, but the fifth move is in the middle, and the eighth move is in the middle. So these are indeed all distinct. They're all different. There's no doubles. So that's a total of 9, and you now have choice E for number 25. Tanner wants to fill his swimming pool with 2 hoses, each of which sprays water at a constant rate. Hose A fills the pool in A hours when used by itself, where A is a positive integer. Hose B fills the pool in B hours when used by itself, where B is a positive integer. When used together, hose A and hose B fill the pool in 6 hours. How many different possible values are there for A? As always, I like to use numbers instead of letters. So I'm going to let this big pool have 600 liters of water. And you can choose any number. I just wanted to choose something that was similar to 6. So I chose 600. So that means hose A, if you have 600 liters and you divide by the rate, or you divide by actually the number of hours, A hours, it will give you the rate in liters per hour. So very similarly for hose B, it's the same story. You take 600 liters and divide by B hours, and that gives you the rate. So let's illustrate this with some numbers, and it will make it very clear. Let's say I'm going to use numbers that obviously are divisible into 600. I'll let A equal 10 and B can equal 15. All right? Now just showing you what this comes out to. If A is 10, that means we've got 600 over 10, and that is 6. 60. Okay? 60. So that means 60 liters per hour. And similarly, if B is chosen to be 15, this becomes 600 over 15. And that is 40 liters per hour. So now you have to understand that they are using both of these hoses at the same time. So hose A contributes 60 liters of water per hour, and hose B would contribute 40 liters of water per hour. So when used together, they would contribute 60 plus 40, which is 100 liters of water per hour. And if you take the pool, which is 600 liters, and divide by 100 liters per hour, you will get 6 hours as the time that it takes to fill this pool. And that is what they have in the question. So I chose these numbers purposely to come out to 6. That wasn't magic. These numbers were chosen on purpose. So what they're asking us for is how many different possible values are there for A? I just let A equals 10, right? That was something that I chose. How many other possible values are there for A? So that involves making a table. My table will be obviously A, B, 600 over A, 600 over B, and all of these have a total of 100, just like I have over here. So I don't really need to keep filling 100 every time. All of these are going to be 100. Okay, so we start plugging away here. That's really all it is, and hopefully we don't have to plug in too long because it's a limited time on a math contest. Now, first and foremost, we have to remember that this is very important, right? So we can't have A equal to 1, 2, 3, 4, or 5, or even 6. Because if you have A equals 6, then immediately this part becomes 100. And then that means that this would contribute nothing. That would have to be 0. But there's no way that can be 0, right? Because if B is 0, this would be undefined. So 6 for a value of A doesn't work. How about 7? If it's 7, this becomes 85.7 approximately. Therefore, this would be approximately 14.3. And these are very easily calculated numbers on any calculator. And if you do this, you get a B value of 42. Okay, so I encourage you to figure that out on your own. And let's keep going. If A is 8, then this would become 75. Therefore, this has to be 25. And therefore, this will be 24. So far, so good. Let's just put check marks behind our integer solutions. This one and this one. Those two are integers. How about 9? If this is 9, then 600 over A becomes 66.66. Therefore, this is 33.33, right? Because the total is 100, remember? And if 600 over B is 33.33, then that means B is 18. Again, another integer solution. So let's keep going here. How about when it's 10? Well, 10, I am confident that it works because I had used that originally. This is 60, this is 40, and this is 15. So that's definitely one of the integer solutions. Keep going like this. How about if it's 11? This becomes 54.54. And this becomes 45.45. And unfortunately, this becomes 13.2. So this is not an integer solution. But how about 12? If it's 12, then this becomes 50. Therefore, this has to be 50, and this is 12. So we've got another integer solution here. Keep going like this. If this is 13, this is 46.15. This is 53.8 approximately. And that would make this guy about 11.1, and that's not an integer solution. If this is 14, this becomes about 42.85. This is 57.1, and unfortunately, this is not going to be an integer. If this is 15, this becomes 40, this is 60, and this is 10. So we got an integer solution. And then at this point, instead of plugging in 16, 17, 18, you should be able to recognize that this is symmetric. This is the middle point, and then everything on that side is going to be the same as this side in terms of the integer values. So 12, 12 was the middle ground, but then you notice this was 10, 5, but then this was 10, 15, and 15, 10 is a solution. So similarly, all of these guys will be solution if you flip them. So 15, 10, 18, 9, 24, 8, and 42, and 7. So if you can recognize that, you can save yourself a lot of time without having to go through every single one, 14, 15, 16, 17, like that. So how many did I get? I got 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 possible values for A and B. What they want is the number of possible values for A. Well, these are the possible values of A. And 7, 8, 9, 10, 12, 15, 18, 24, and 42. 9 of them. So therefore, number 25, the answer is C. Ten circles all are the same size. Each pair of these circles overlap, but no circle is exactly on top of another circle. What is the greatest possible total number of intersection points of these 10 circles? Well, you are definitely not going to draw 10 circles and try to count all the intersection points, because as you can see from the answer choices, they're a lot. I mean, the smallest is 40, goes up to 110. That is not a good strategy for this question at all, to try to draw 10 circles and then see how many intersection points there are. The better strategy is to make a little list, number of circles, number of intersection points, and see if you get some sort of a pattern that you can extrapolate all the way till 10. And hopefully we won't have to do too many. So let's just start with the very first one, which is 2 circles. If you have 2 circles, as you can see, the maximum number of intersection points is 2. So we got 2 right there. Okay, so far, of course, way too early to look at any kind of a pattern. So let's try 3. Say 3 circles. And remember, they're all the same size, so I'm going to try to draw them the same size. Okay, that's 2. I need one more, but I got to draw it in a way that I maximize the number of intersection points. So I think it's maximized if I do like that. Okay? So I got 1, 2, 3, 4, 5, 6 intersection points. Okay, for 3 circles, the maximum is 6. It was 2 for that. Okay, still have no clue of any kind of a pattern. So let's try 3. 3 circles. So let's see here. We got 1 circle, 2 circles. The third one I'll draw in the same way. And then I gotta maximize, right? So if I want to maximize my circle, I will do that. That will give me my max. Now I apologize, they're not exactly the same, but you kind of get the idea. Okay, let's count now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so for first 4 circles, it's 12. It doesn't look, I don't see a pattern here yet. Maybe you do, but I don't. So I'm going to do one more, and my hope is that with 5, I can see a pattern. Okay, let's draw 5. So just continue in the same way, actually, that I've been drawing the circles. That was for 2. I think this was the way I drew the third one. The fourth one, I drew it like that, and then I'm going to draw a 5th one. Okay, so this is the challenging part. I got to draw a 5th one, and I think this would maximize it. Yeah, well, it's got to be the same size anyways. Okay, I'm pretty sure that maximizes it. Okay, let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, 20. And I definitely don't want to draw another circle here. I think I can figure this out. So between 2 and 6, the difference is 4. between 6 and 12, the difference is 6. Between 12 and 20, the difference is 8. So, do you see a pattern here? I do. The difference goes up by 2 each time. So that means for the other ones, I think I can squeeze it in. 6, 7, 8, 9, and 10. For 6, it would go up by 10, right? Because the difference is going up by 2 each time. So that would mean this is 30, just 30. For 7, the difference would go up by 12. So that would be 42. For 8, the difference would be 14. So that would be 56. For 9, the difference is 16. So that would be 72. And for 10, the difference will go up by another 2 to 18, and that would be 90. There you go. The answer is 90. So you see how I did that? Number 25, therefore, is D. The positive integers are arranged in rows and columns below. Row 1 is 1, row 2, 2, 3, row 3, 4, 5, 6, row 4, 7, 8, 9, 10, row 5, 11, 12, 13, 14, 15, row 6, 16, 17, 18, 19, 20, 21. More rows continue to list the positive integers in order, with each new row containing one more integer than the previous row. How many integers less than 2,000 are there in the column that contains the number 2,000? Well, what we want to do is first get some sort of a general formula, and that will help me understand where does this 2,000 actually show up, what row. Right now I'm not really sure. So what I'm looking at is what is my formula for that largest number, because that immediately comes striking as the sum of the digits. So for example, that last number is obviously the sum, right? Because 1 is equal to just 1, but 3 is equal to 1 plus 2. 6 is equal to 1 plus 2 plus 3. 10 is equal to 1 plus 2 plus 3 plus 4. You see how there's a pattern there? I immediately recognize that pattern. So that means if you have row n, the last number of that row, let's just say it's way out here, is going to be the sum of all the numbers from 1 until n. Okay? So for example, it will be 1 plus 2 plus 3 all the way until n. And it's a grade 7 contest, so I'm not sure if you know this formula, but it's number 25. That's why it makes it difficult, I guess. It's the formula as n times n plus 1 divided by 2. Okay? Anytime you have the sum of consecutive numbers from 1 to n, you can just use that formula. So let's prove that. For row 6, 6 is my n in this case. Well, if I put 6 into this, I get 6 times 7 divided by 2. And that is 21. There you go. What about for 5? When n is 5, I get, using this formula, I get 5 times 6 divided by 2, which is 30 divided by 2, which is 15. There you go. Let's do one more. I'm sure you're convinced, but let's just do one more. When n is 4, using this formula, you get 4 times 5 divided by 2, which is 10. And as you can see. So generally speaking, if the row is the nth row, the very last term in that row will be n times n plus 1 over 2. Okay, so that is very helpful. Now I've got to figure out in what row approximately is this number 2,000. I don't know. Well, I'm also not sure where in the row it is. Is it the very last number, or is it the very first number of the row, or is it somewhere in the middle? I don't know. So what I'm going to do is just assume that it's somewhere, it could be the last one. Let's just say, I don't know, but it'll give me at least an approximation. So I'm going to say, maybe it's the last one. It'll give me an approximation of what n is. So if I do this, it's n times n plus 1 is equal to 4,000. And again, it's just an approximation, so what we can do is, this is very similar to n times n, right? So that's like n squared. So just take out your calculator, and calculators are allowed on the Canadian contest. Take the square root of 4,000. And when you do, you get approximately about 63. Okay, that helps me. It may not be 63, but it helps me. At least it's in the vicinity. So let's figure out a possible scenario. Let's say n is 63. If n is 63, then what is my last number? Well, I just use that formula. So I get 63 times 64 divided by 2. And when you do, you get 2016. So that means in the 63rd row, the very last number is 2016. Okay, that's very helpful actually, because that means that the number 2000 is going to be in the 63rd row. How do I know that though? Well, because every row, the row number tells you how many numbers are in it, right? The first row has 1, second row has 2, sixth row has 6. So the 63rd row is going to have 63 numbers in it. And that means that 2000 has got to be in there somewhere. Yeah, dot, 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 I'm not going to list them all. And the very first number, well, it's going to be 2016. You got to be a little bit careful here. 2016 minus 63, but that doesn't give you, you have to add 1. Okay, you got to be a little bit careful. 1954, right? Because 1954 to 2006 inclusive is 63 numbers. Okay, so I just want you to make sure that you don't, make a mistake by one number that could mess up the whole question. And as you can see, the answer choices are very similar because they're anticipating that. Okay, so we got a pretty good result here. You got 1955 and so on, right? Dot, dot, dot. So we know that 2000 is in the 63rd row. Okay, but they want you to figure out what column also. Okay, you say, oh boy. Well, I got the row, but they want me to figure out the column. All right, fine. Well, how do I do that? Well, it shouldn't be that bad. Let's just talk about this. The very first column is this one right here, right? Right there. And in that column, you're going to have the same number as the row, for example. If I asked you how many numbers are in that column, well, you can count them. 1, 2, 3, 4, 5, 6. But the good news is, all you have to do is just look at the row number. It'll be 6. So if I asked you how many numbers are in the first column all the way down to this guy, the answer is going to be 63. So there's 63 numbers in this column. Now, if I asked you how many numbers are in the next column, just in this first 6 rows, well, you can count them, 1, 2, 3, 4, 5, but as you can clearly see, it's 1 less. So same thing, if I asked you how many numbers are in this column, it's 1 less than the 63, so it's 62. Does that make sense? I hope so. So if I asked you how many numbers are in the column that contains the 2000, well, we have to first figure out where is the 2000 in terms of its placement. Well, this is obviously the first term. This is the second term. 2000, if you keep counting like that, it'll be the 47th term. Right? You can count it. It's pretty straightforward. Or what you can do is you can just take 2000 and subtract from it 1953. Okay, you can do that as well. 2000 minus 1953. Not 1954, 1953. And if you do that, you also get 47. It's the 47th term in that row. So, same logic. The first column contained 63 numbers. The second column contained 62 numbers. The third column would contain 61 numbers. So the 47th column you just have to keep subtracting. Or you can have a little bit of a trick. Let's say this number is x, right? Notice this number and this number add up to 64. This number and this number add up to 64. So that means this number and this number have to add up to 64. And that's a little bit of a trick. And therefore that number must be 17. Okay? Now, just when you think you're done with the question, there's one final trick. Please do not circle 17. You say, well, why? Isn't that the right answer? No. Read the question carefully. How many integers less than 2,000? So they don't want you to include that 2,000. They want you to include all the column above it. See what I mean? There's 17 numbers in that column if you included the 2,000, but they want you to count only the numbers less than 2,000. So take out that 2,000, that leaves you with 16 numbers. It's a great question, number 25. The answer is D. A box contains a total of 400 tickets that come in 5 colors: blue, green, red, yellow, and orange. The ratio of blue to green to red tickets is 1 to 2 to 4. So I'll call it x to 2x to 4x. The ratio of green to yellow to orange is 1 to 3 to 6. So the ratio of green to yellow to orange is 1 to 3 to 6, so I will write Z, 3Z, 6Z. What is the smallest number of tickets that must be drawn to ensure that at least 50 tickets of one color have been selected? All right. So the first thing we have to do is find out the distribution of these tickets, considering that they all add up to 400. Well, Z represents the number of green tickets, but so does 2x. So that means that 2x is equal to Z. If 2x is equal to Z, that means x is equal to Z over 2. So put that here. 4x would be equal to 2Z. So put that here. And then 3Z would be equal to 6x. So put that here. And 6Z will be equivalent of 12x. So put that here. So I can add all these guys up. And if I do, that will equal 400. So x plus 2x plus 4x plus 6x plus 12x is equal to 400. So what does that give me? 3, 7, 13, and 25. So 25x is equal to 400. So that means x is 16. So plug those numbers back into here. So that means we've got 16 for blue, we've got 32 for green, 4x is 64, 6x is 96, and 12x is 192. So that's the number of tickets of each color. Now our task is the final sentence. What is the smallest number of tickets that must be drawn to ensure that at least 50 tickets of one color have been selected? Notice the spelling of the word color. That you can tell it's a Canadian math contest. All right, so let's use extreme case scenarios here. We want to use the smallest number of tickets. Now, some of you might say, well, just choose 50 tickets. That's the smallest number, and it's the smallest of the answer choices. But here's the thing. If I choose 50, it doesn't ensure that I get 50 of the same color. Let's say I chose 50, but it was a few of them were green, and a few of them were red, and a few of them were yellow. That doesn't ensure. I have to guarantee. Now, how do I do that? And this is the way you do it. First, what you do is you select all of the blues. So that's 16 of them. So we've exhausted the blues. Now we select all of the green. That's 32. We're done. We've taken all the greens out. Right? Now, we can't choose them, meaning we can't look and see that we're choosing them. But what I'm saying is this is the extreme case scenario that just by chance, when you selected 16, all of them happened to be blue. Then you selected another 32, and all of them happened to be green. It's an extreme case scenario. Now what we do is we say, okay, I'm not guaranteed of having the same color. I'm going to select 49 now of the red. And just by some chance, they all happen to be red. Then I'm going to select another 49 tickets, and by chance, they're all going to be yellow. And then I'm going to select another 49, and by chance, they're all going to be orange. The reason I'm doing it like this is because I have to guarantee that when I choose a certain number of tickets, that there's going to be 50 of the same color. This scenario does not produce 50 of the same color. You see what I mean? So this scenario is possible. And we have to look at any extreme case scenario where it's possible to not have 50. This is a possible scenario where I chose 16 blue, I chose 32 green, 49 were red, 49 were yellow, and 49 were orange. So let's add these up, and when you do, you get 195. So far, in this extreme case scenario, we don't have 50 of any one color, but the very next ticket that's chosen will push me to 50. It won't be a blue or a green because those are exhausted. Those have already been all selected. But the very next ticket I choose must end up being either a red, yellow, or orange because there still are some of those left, right? Because 64, 96, and 192 are the total, and I only chose 49 of each of them. So the very next one, let's say if it's an R, a red ticket, boom, I've got 50 of them. If the very next one happened to be a yellow, I've got 50 of yellow. If the very next ticket happened to be an orange, I've got 50 oranges. Oh, 50 orange tickets. So 195 plus the very next ticket, and that would be 196. So it's a good little challenge in terms of counting. And therefore, number 25, the answer is D. On a coordinate grid, Paul draws a line segment of length 1 from the origin to the right, stopping at 1, 0. He then draws a line segment of length 2 up from this point, stopping at 1, 2. He then continues to draw line segments to the right and up, increasing the length of the line segment he draws by 1 each time. One of his line segments stops at point 529, 506. What is the end point of the next line segment that he draws? Well, if you look at this diagram, they've drawn obviously just the first few. And in particular, if you look at any point xy, what will it be? Well, the x-coordinate looks like it'll be 1, and then 1 plus 3, 1 plus 5, and so on, right? So the x-coordinate will be 1 plus 3 plus 5, dot, 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 and so on. Whatever we end up until. And let's say we go until n. I don't know how far we're going, right? When I get to here, I'm not sure yet how far I have to go. But that's what the x-coordinate will be. The y-coordinate, if you look at it, it'll be going up. So 2 plus 4 plus 6 and so on. So 2 plus 4 plus 6 and so on until we get to some value. And again, I don't know what it is, so I'll just call it m. But one thing I do know is that n and m are very close together. They're only 1 apart. For example, if n was, say, 5, m would be 6, right? So I'm not 100% sure yet, but n and m differ by 1. So let's just say n is equal to m minus 1. It could be off by 1. It could be n is equal to m plus 1, but this is a pretty decent start. Okay, so now they give us the big clue that eventually we're getting to 529 and 506. All right. Well, there's a quick way of doing this question. There's a longer way. The longer way sort of explains it a little bit better. And I'm going to do it the longer way just because I want to explain it a little bit better. But on a math contest, you do it in the shortest way possible. So because I want to explain it, I'm going to take this point, 529, and in a very straightforward way, assign this to be x and this is y. So this 529, since it's x, I'm going to use that formula. So 529 is equal to 1 plus 3 plus 5 plus ... until some n. And 506, since that y is 506, that's going to be 2 plus 4 plus 6 plus ... all the way till some m. All right. Now, you guys have a calculator. It's allowed on the exam. Some of you can easily just do this on a calculator. You can just get out in 1 plus 3 plus 5 plus 7 plus 9 plus 11 ... Keep going until you get to 529, and you'll be able to figure out your n. And then you can do the same thing here, 2 plus 4 plus 6 plus 8 plus 10, and you can easily get up to m. But these are kind of big numbers, right? They're not extremely big, but they're sort of big. So what I'm going to show is a formula. The first formula I'm going to show you is this one right here. When you have this kind of scenario, it's not consecutive numbers, it's consecutive even numbers. So we can factor out the 2. And when you do, you get 1 plus 2 plus 3, like that. And that is consecutive numbers. The 1 plus 2 plus 3 part. So that goes all the way until now m over 2. And this part has a formula. And some of you may know it, some of you may not. It's in grade 7. So you're in grade 7, so you may not know that the sum of consecutive numbers ... until n is equal to n times n plus 1 over 2. All right. So using that formula here, this part becomes m over 2 times m over 2 plus 1 all over 2. All right. So that basically, these 2's cancel out. So you just have m over 2 times m over 2 plus 1. And that, of course, equals 506. Now, at this point, I do not encourage you to multiply it out and use a quadratic, all that stuff. Just use inspection. Get out your calculator, take the square root of this, and see what two numbers multiplied by each other equal 506, right? And those two numbers are consecutive. So do a little bit of fiddling around. When you take the square root, you'll see that it's about 22 point something, right? So I think that m over 2 is possibly 22. Well, let's see. Take out a calculator, take 22, multiply it by 23, and indeed it is going to be 506. So there you go. M over 2 is indeed 22. So that means m is 44. Perfect. All right, now go back. Remember in the beginning I said that n is 1 away from m. So if m is 44, n is perhaps 43. So now I've got to go back to this formula and figure out what is x. Okay, no problem. X is 1 plus 3 plus 5 plus ... all the way until n, and that n I have chosen to be 43. Again, I would like to show you a formula. You can do this in a calculator without a formula. Formulas are not necessary, by the way. I'm not saying you need to, but it just makes it faster and also helps you learn a little bit more. The formula for this now, these are not consecutive numbers. These are consecutive odd numbers. That is not going to be this formula. It's going to be something else. And that formula is a little lesser known. This one is very well known. But the consecutive odd numbers, that one is a little lesser known. That one is n plus 1 times n plus 1 all over 4. And even if you didn't know this formula, like I said, don't worry about it. You can easily do this on a calculator. To 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 and so on all the way up until 43. If you do that, you get 484. Now you say, oh, that's not 529. Okay, no problem. All that means is that I just have to add one more because n is not 43, n is most likely 45. So add another number, and when you do, you get 529. So let's illustrate this in a very, very brief diagram. So that means we had a scenario as follows. We went this way, we went this way, right up, right up. We kept going right up, right up. And then what happened was, let's just fill this in. We had 41 here, 42 here, 43 here, 44 here, and then 45 here. That's how we got to this point right here, which was our 529, 506. And now if we keep going, we're going to go 46 up to get to this point. And they're saying, what are the coordinates of that point? Well, if you go up 46 from this point, the x-coordinate doesn't change. It just remains 529. But the y-coordinate definitely changed. You have to add 46 to the y-coordinate. And when you do, you get 552. So that is going to be the end point of the next line segment that he draws. And therefore, number 25, the answer is A. Two different two-digit positive integers are called reversal pair if the position of the digits in the first integer is switched in the second integer. For example, 52 and 25 are a reversal pair. The integer 2015 has a property that it is equal to the product of three different prime numbers, two of which are a reversal pair. Including 2015, how many positive integers less than 10,000 have this property? All right, well, the first thing is just to look at 2015 when you break it up into prime factors. It's 5 times 13 times 31. And obviously, these are the ones that make up that reversal pair, 13 and 31. So we want to have an integer less than 10,000 that can also be written as a product of three different prime numbers. So prime 1, prime 2, prime 3. And two of them have to be a reversal pair. All right, so the first thing to do is write out all the primes, and in particular, the primes that are two digits or less, right? So that's what this is, and there's 25 of them, and this is one of those questions that illustrates the importance of memorizing the prime numbers, at least, the first 25 or so. So in order to get a situation like this, I've got to get some P1 times a reversal pair. Now let's list our reversal pairs. 13 and 31. Looking entirely at this list right here. What two numbers are reversals of each other? Another one from that list is 17 and 71. Another one from that list would be 37 and 73. And I believe there's one more that I can get, and that's 79 and 97. So these ones would fit. And that would allow us to create this sort of a scenario. Okay, so let's work with these one at a time. So first, let's talk about P1 times 13 times 31. How many such scenarios can I get? All right, well, the number itself is n, and n has to be less than 10,000. So that means that 10,000 has to be less than n. Now, let's look at what is 13 times 31. That's 403. So this number has got to be less than this quotient. And this is approximately 24.8. So that means that this P1 has got to be less than 24.8. Okay, so let's list which prime numbers are less than 24. 2, 3, 5, 7, 11, 13, 17, 19, and 23. So that's 9 of them, right? But here's the thing. One of them is not allowed. Which one? This one. Why? Because it has to be three different. If I had to put a 13, it would be, two of them would be the same. So of those 9, the 13 is the only one I can't use, so I can use the other 8. So I've got 8 possible ways of making this n. All right? Let's move forward in the exact same way. So now we move forward to the next guy, which is P1 times 17 times 71. Again, n is equal to P1 times 17 times 71. And the number n has to be less than 10,000. So we got to divide 10,000 by the product 17 times 71 to try to figure out an approximate value for P. That is 1207. So that means that, what is that, 8.2 8.2 approximately. So that means P1 has to be less than 8.2. Well, let's list the primes that are less than 8.2. 2, 3, 5, and 7. And all of these are allowed. None of these are going to give you a double. So there's 4 of these guys. So let me just put the 4 there. 4 here, 8 here. All right. Okay, let's keep on going. It's in the exact same way for the next one. The next one is 37 and 73. So this time my n is P1 times 37 times 73. Again, 10,000 divided by this product, 37 times 73, which is 2701, and that is 3.7 approximately. So P1 has got to be less than 3.7. And the only primes that could match that would be 2 and 3. So that gives me 2. And then we got one last one. And that last one is this guy right here. It's this one right here, 97 and 79. So 79 times 97. Again, 10,000 divided by this product, which is 7663, and that is approximately 1.3. So that means P1 has got to be less than 1.3. Well, there's no prime number less than 1.3. So here, nothing. So we now total up the cases. 8 here, 4 here, 2 here. That total is 14. 14, therefore, is the answer to this question, number 25. That would be choice B. In the triangle shown, the first diagonal line, 1, 2, 3, 4, begins at 1, and each number after the first is 1 larger than the previous number. The second diagonal line, 2, 4, 6, 8, begins at 2, and each number after the first is 2 larger than the previous number. The nth diagonal line begins at n, and each number after the first is n larger than the previous number. In which horizontal row does the number 2016 first appear? All right. Let's discuss this a little bit. Let's say I said to you that I want you to tell me, when does the first 10 appear? Well, the first 10 obviously appears here. I mean, how could you figure that out, though? Well, it appears in this diagonal. So you can say, well, the diagonal starts with 2. So 10 is a number that I'm interested in. I'll divide by 2, and that's 5. So it appears here, the 5th entry in that diagonal. But that's not the row number. As you can see, it's in the 6th row. And how do you get the 6th row? Well, you take that 5 and you add to it this number minus 1. So 2 minus 1. And that would give you the 6th row. Very similarly, if I said to you, when does the first 12 appear? Okay, well, it appears obviously in that diagonal. So that diagonal begins with a 3. So you take the number 12, divide by 3, and that's the 4th entry in that row. But it's not the 4th row. It's actually in the 6th row. How do you get the 6th row? Well, you take this 4 and add to it 3 minus 1. And that would give you 6. So in a very similar way, we have to do that, but this time our number is 2016. So this is the table. We first have to figure out the factor of 2016. So this is factor of 2016. And that represents n, which will be the same n as what they talk about in the question. So for example, if n was 4, it would be this diagonal. If n was 5, it would be this diagonal, and so on. The next column in this table is the position in the diagonal. So for example, if I said to you, what position is that in this diagonal? Well, it's the 4th position, right? 1, 2, 3, 4. If I said to you, what position is this in the second diagonal? Well, it's the 1, 2, 3, 4, 5th position. So I will call that D. And then finally, we have to figure out the row. And the row is given by D plus n minus 1, exactly what I did over here. So a quick example, we'll just start with 2016, and I guess those will be good enough examples. There's a lot of factors, right? 2016, if you break it up into its prime factors, is 2 to the power of 5 times 3 to the power of 2 times 7 to the power of 1. So as you can see, there's a lot of factors. That's a 6. The way you do it is you take the number 5, you add 1, they take this 2, add 1, and you take that 1 and you add 1, and that multiplied together gives you the number of factors. 6 times 3 times 2 is 36. So there's 36 factors. So got a little bit of work on our hands, but it's okay. Let's start. 1, 2, 3. These are the factors of 2016. 1, 2, 3, 4, 6, 7, 8, 9, 12. 14, 16, 18, 21, 24, 28, 32, 36, 42, 48. And we keep on going here. 56, 63, 72, 84, 96, 112, 144, 168, 224, and so on. And if we need to go further, we will, but I think we should be able to figure out a pattern. At least I hope so. Okay, so let's go to this table. When an n is 1, the position in the nth row is 2016 divided by n. That's how you would get it. So I'm going to actually write that in red, because 2016 divided by n is how we're going to get d. Well, in this case, it's pretty straightforward. That's just 2016. Okay, now the next one is d plus n minus 1. So this is my d, this is my n, so that's just going to be 2016. Let's do the next one. 2016 this time divided by 2 is 1008. Now my row R would be d, which is 1008, plus n minus 1, which is 2 minus 1, which is 1, so that'd be 1009. Now our goal is to get this number to be as low as possible. So let me put that in red. Lowest. The lowest possible number for this column of the table. That's going to be the answer to the question. So you just keep doing this. For 3, it'd be 2016 divided by 3, which is 672. And then the row would be 672 plus n minus 1. N is 3, so that would be plus 2, which is 674. So now that you are an expert, I don't need to walk you through it. I'll just fill it out. 504, 507. And let's just see what the answer choices are. Oh, they're in the less than 100, so we got to keep going here. 336, 341, 288, 294, 252, 259, 224, 232, 168, 179, 144, 157. Okay, the numbers are getting smaller, so that's good. 126, 111, 112, and 129. Sorry, that was 141. 112 is 129. And then 96, 116, 84, 107, 72, 99. Is 99 one of the answer choices? Nope. Okay, no problem. We're getting close though. 63, 94. That is one of the answer choices. 56, 91, 48, and 89. And then 42, again 89. and then 36 and 91. Aha, it goes back up now, and I have a feeling it's going to go back up again. So 32, 94, there we go, it does. 28, 99, 24, 107. Yeah, it's pretty much going up in the same way. If you notice, this is the same as that. 89, 91, 94. Yeah, okay. So that means we hit rock bottom here. 89. That's the lowest number in that column. So that's the answer to the question. Number 25, 89, that would be E. Ashley writes out the first 2017 positive integers. She then underlines any of the 2017 integers that is a multiple of 2, and then underlines any of the 2017 integers that is a multiple of 3, and then underlines any of the 2017 integers that is a multiple of 5. Finally, Ashley finds the sum of all the integers which have not been underlined. What is the sum? This is a very interesting question. So initially we have 1 plus 2 plus 3 all the way up until 2017 if you were going to add up all the numbers. And throughout this question, I'm going to use a formula that I'm sure some of you or most of you may know. That is, if you add up all the numbers 1, 2, 3 up until n, that is equal to n times n plus 1 divided by 2. So in the beginning, I've got all these numbers until 2017. So using this formula, that's going to be the sum 2017 times 2018 divided by 2. Correct? And that is 2035153. All right. So now we have to take away all the numbers that are divisible by 2. Because remember, all the numbers that are multiple of 2 she underlines, and at the end we have to figure out the sum of all the numbers which have not been underlined. So essentially you're just removing those numbers. All the numbers that are multiples of 2 are of the form 2, 4, 6, 8. And then we have to figure out what's the final number. Well, it'll go all the way up till 2016, right? Because 2017 is not a multiple of 2. Okay, well, how do you add up these guys? Factor out a 2. And then you'll get 1 plus 2 plus 3 plus ... until 1008. And then you can apply that formula. It'll be 2, but that is just going to be using that formula. So 1008 times 1009 all divided by 2. And this is 17072. But remember, in the sum, we have to subtract these guys because these numbers will be underlined. And at the end, we have to add up the numbers that were not underlined. Okay, then she underlines multiples of 3. 3, 6, 9, and so on. And then we have to figure out how far do we go when we underline multiples of 3. And you go until 2016 again. Well, how do I figure out this sum quickly? Factor out a 3. And when you do, you get 1 plus 2 plus 3 plus ... until 672. Again, we'll use this formula. So it's 3, but then this is just going to be using that formula 672 times 673 divided by 2. And this big long number is 678384. And remember, these guys we have to subtract because these were underlined. And the underlined numbers are not going to be counted at the end. We have one more, and that's 5, multiples of 5. So 5, 10, 15, and so on, right? And that's going to go all the way till 2015. Again, by now I think you're an expert. Factor out the 5. That'll be 1 plus 2 plus 3 plus ... 2015 divided by 5 is 403. Okay, now let's use the formula again. So we have basically a 5 out front, And then we have 403 times 404 divided by 2. And that is 407030. And we have to subtract these. Okay. Now, are we done with the question? And the answer is a big no. It's not that simple. We've done everything correctly, but there's a few more steps. All right, well, what are the steps? Well, I'll explain. So far, everything's fine, but you see there's a 6 there? There's a 6 here also. So that means we subtracted the 6 twice. And similarly, any number that is a multiple of both 2 and 3 would have been subtracted twice. And therefore, since we subtracted those numbers twice, we had to add them back once, right? I subtracted 6, I subtracted 6 again. So I've got to add back 6. You see what I'm saying? So subtract, I've got to add. So any number that is a multiple of 2 and 3, I subtracted twice, I've got to add it back. So what are those numbers? Multiples of 2 times 3 are multiples of 6. So 6, 12, 18, and ... So we go all the way up until 216, because that's the largest multiple of 6. All right, here we go. Again, factor out the 6, and we get 1 plus 2 plus 3, all the way up until 2016 divided by 6 is 336. So, again, we use our formula. 6 times 336 times 337 divided by 2, and that is going to be 339696. And this one, remember, we have to add back. We're adding one of those back, one of those multiples of 6. We had subtracted it twice, so we got to add it back once. All right, so now we have to do the exact same thing, but this time for multiples of 2 and 5. For example, 2 and 5 is 10, right? So there's a 10 in here because it goes 2, 4, 6, 8, 10. And there's a 10 in here because it went 5, 10, 15. So as you can see, we subtracted the 10 here, we subtracted the 10 there. In a very similar way, because we subtracted the 10 twice, we have to add it back once. So the same kind of story. 10 plus 20 plus 30, all these guys were subtracted twice, so we have to add them back once. So we're going to go up to, I believe, 2010. So factor out the 10, we get 1 plus 2 plus 3 plus ... up until 201. And that would give me 10 times 201 times 202 divided by 2, and that is 2031010. And remember, we're adding this guy. And then there's one last one that's a double. We had taken care of multiples of 2 times 3, which are 6. We had taken care of multiples of 2 times 5, which is 10. We now have to take care of multiples of 3 times 5, which is 15. If you notice, in this list up here, 3, 6, 9, 12, 15, there's going to be a 15 in there. And there's a 15 in here. So we had essentially subtracted the 15 twice. So in the same way, we've got to add it back once. So 15, 30, 45, all these multiples of 15 have to be added back once. And it goes all the way up until 2010 again. 2010 is a multiple of 15. Factor out the 15, 1 plus 2 plus 3, all the way up until 2010 divided by 15 is 134. So using our formula, we got 15 times 134 times 135 divided by 2. And this number is 135675. And that number, of course, we have to add back. Okay, are we done? The answer is no. We have one more number that we have to either add or subtract. And this one, I think some of you might have been able to figure it out, but if you haven't, no problem. It's numbers that are multiples of 2, 3, and 5. Multiples of 2, 3, and 5. So the smallest one would be 2 times 3 times 5, which is 30. And what's interesting about 30 is that it appears in all three lists. It would appear in this list somewhere in here because it's a multiple of 2. It would appear in here somewhere because it's a multiple of 3. It would appear in here because it's a multiple of 5. So if you notice, we subtracted it here, and we subtracted it here. But then we added it back here because 30 is a multiple of 6. We added it back here because 30 is a multiple of 10. We added it again back because 30 is a multiple of 15. So essentially we subtracted it 3 times and we added it 3 times. So we haven't really taken care of it yet. You subtracted 30 3 times, you added it back 3 times. So we have to subtract it once at least. So that's what we're going to do. We have to now subtract the multiples of 30. So 30 plus 60 plus 90, ... And then what number are we going all the way up until 2010 again? 2010 is a multiple of 30, interestingly. So you are an expert now. Factor it all out. And then 2010 divided by 30 is 67. So using our formula, we got 30 times 67 times 68 divided by 2. And that number is 68,340. And we are doing what to this? Subtracting once. So that's probably the most challenging part of the question. Okay, now we got all our numbers, all of these numbers here, right? We have to add them all up. We'll add and subtract. So we got this one, subtract that one, subtract this one, subtract this one. Then we have to add this, add that, add this, and finally, we have to subtract this. And when you do all of that math, you get 5,42708. That is your number. 5,42708. And that is choice A for number 25. In the triangle, each of the numbers 1 through 8 is placed into a different circle. The sums of the numbers on each of the 3 sides of the triangle are equal to the same number s. The sum of all of the different possible values of s is. I'm going to label this now A, V, W, B, and then Z, C, X, Y. A, B, C purposely chose as the vertices. So that sum is either A plus V plus W plus B, or that sum is the bottom, which is B plus Z plus C, or the sum is the other side, which is A plus X plus Y plus C. Now, all of those are equal according to the question stem. Now, let's add them up. If I add them up, I get 3S. Remember, I'm adding these 3. Let's write it over here. It gives me a little bit more space. 3S. And we add it up, you get A plus V plus W plus B plus Z plus C plus Y plus X. And then you also get an additional A, an additional B, and an additional C, like that. Now this, right, just those guys are basically all of those, and those are between 1 and 8. So it's like adding all the numbers from 1 to 8. And when you do, you get, what, 8 times 9 divided by 2, which is 36. And then you've got this a plus b plus c. Put the 36 on the other side, and therefore, if you factor out a 3, you'll get s minus 12. So that means a plus b plus c is some multiple of 3. That is the conclusion. So a plus b plus c, what are the possible multiples of 3? Well, the smallest it could possibly be is 6, 1, 2, 3. So 6, obviously, 9, 12, 15, 18, 21. What's the largest it could be? 6, 7, and 8, which would make it 21. So that's it. This is the range. So now I've got to figure out, through trial and error, how to place this. And I'll put in a diagram. And after you fiddle around with this, you will see that these are the only ways of making this work. Now I'm interested in what is the value for a plus b plus c. Well, in the first one here, as you can see, it was a, b, and c, so that was 9. So that one works. The second one, it was this, this, and this, which is 12. So that one worked. And then the third one, 2, 5, and 8 is 15. And the last one, 6, 7, 8, that's the largest one actually. So that's 21. So this and this, for some reason, didn't work out. Okay, at this point, we're done with the question, but let's just explore why these two didn't work, because I think that's important to figure out why. If a plus b plus c was 6, then if you substitute it back into here, you get that 3s minus 12 is 6, and therefore s minus 12 would be equal to 2, therefore s would be 14. So that means that this guy down here, this b plus z plus c, that one would have to be 14. But since a plus b plus c is 6, that means we've chosen 1, 2, and 3, like that. And the largest, therefore, b plus c could be was 2 and 3. And therefore, if we did this math, z would have to be 9. And z can't be 9 because our numbers only go from 1 to 8. There's no way to make z the 9. So z, there is no 9. So this obviously does not work out. That's why this a plus b equals 6 is invalid. So no, not possible. Now let's talk about the 18. This guy right here. Okay, same story. A plus b plus c is 18. That means 3s minus 12 is equal to 18. That means s minus 12 would be 18 divided by 3, which is 6, and therefore s would be 18. Okay, again, look at that bottom row, b plus z plus c. b plus z plus c would be 18. And we are going to probably have to choose some large numbers to make this possible. But another thing you can do is just compare those. Since in this particular example they're equal, that means that a plus b plus c is equal to b plus z plus c. The b's cancel and the c's cancel, so you're just left with a is equal to z. But that's not possible. Why? Because each of the numbers is placed into a different circle. You can't repeat the same numbers. No two numbers can be the same. So this, again, is invalid. So the 18 is not possible. So as you can see, it takes a little bit of trial and error in math to come up with the right answer to a relatively challenging question for grade 7. So the only valid values for ABC were 9, 12, 15, and 21. We're going to substitute each of those back into here to get the values for S. And when you do, plug each of these in for ABC and solve for S, you get the following values for S. You get 15, 16, 17, and 19. And now they want you to add those up So the sum obviously would be 15 plus 16 plus 17 plus 19, and that totals 67. And that is the answer to the question number 25, which is E. An 8 by 8 by n rectangular prism is made up from 1 by 1 by 1 cubes. Suppose that A is the surface area of the prism and B is the combined surface area of the 1 by 1 by 1 cubes that make up the prism. What is the sum of the values of n for which b over a is an integer? I will first start off with a simple example. Let's say n is 2. And hopefully this example will make you understand how to approach this question. So in this case, if n is 2, it will be an 8 by 8 by 2 dimension rectangular prism. And that area is 128. Now it's made up of these unit cubes. Each has an area of 1, so it'll be 128 unit cubes in this scenario. Now the surface area, which they are calling A, of the prism will be as follows. It'll be 2 times 8 by 8 plus 2 times 8 by 2 plus 2 times 8 by 2. So I just drew what it could look like, that prism. Okay, so let's figure this out now. This would be, in terms of numbers, 192. Now let's figure out B, which they are calling the combined surface area of the unit cubes. Well, there's 128 of them, and each of them would have a surface area of 6, since it's just basically a unit cube with each side being 1 by 1. So there you go. So that would mean 128 times 6 is 768. So what is B over A in this case? B over A would be 768 over 192, and that is 4. Is that an integer? Yes. So that is how we approach this question. Now let's do the exact same thing, but instead of n being 2, n is just n. So now we have 8 by 8 by n, and that is 64n. That is the number of unit cubes that make up this particular prism. Our surface area of the cube would be 2 times, again, 8 times 8. That's the bottom of the base of the prism. Then it would be 2 times 8 times n this time, plus 2 times 8 times n. So this is 128 plus 32n. Okay. Now B, well, that's very easy. That's just going to be the number of unit cubes, which is 64n, times 6, which is just 384n. Okay, so now what is my B over A? It is 384n over 128 plus 32n. I think I can divide through by 32, and when I do, I get 12n over 4 plus n. All right, so this is very, very nice. I think I can work with this without too much problem. I've got to start plugging in values of n so that this becomes an integer. Okay, I'm sure I can do that. Let's make a table and proceed. So we got n, and then we have 12n over 4 plus n. So this is, at this point, just plug and play. Let's try 1. When you get 1 for n, you get 12 over 5. Is 12 over 5 an integer? No. You try 2. That's 24 over 6, and that is an integer because that is equal to 6. So we circle that. That was actually the one I did in the example. I used n equals 2. So we know that's going to be an integer. And you just keep going like this. 3, and it's going to be 36 over 7. That's not an integer. And then 4. 4 is 48 over 8, and that is an integer. It is equal to 6. So circle 4 as a value for n. And you just keep going like this. So I'm not going to bore you by going through every single one. I'm just going to write the ones for which this becomes an integer. And it is time consuming, but that's the way it is since it's number 25. 8 works. It gives you 96 over 12, which is equal to 8 Therefore, that works in terms of giving you an integer value. The next one that works is 12 for the value of n. It gives you 144 over 16, which is equal to 9. 9 is, of course, an integer. The next one that works after a lot of numbers that don't work is 20. You have to get all the way up to 20. 240 over 24, and that's 10. And then you get really painful. You've got to keep trying until 44 to get the next value of n. And that gives me a integer value of 11. And at that point, it's finished, thankfully. And now you just have to add up the values of n that worked. So 2 plus 4 plus 8 plus 12 plus 20 plus 44. And that's 90. So that is the answer. And that's B. Now you might say, well, how do you know that you have to stop at 44? Why didn't you just keep going here, 45, 46, and so on? Because if I did, my sum would be greater than 90. It would be much greater than 90. It would be at least 45 greater than 90, and there's no answer choice that is that big. So you can be confident that 90 is indeed the right answer. So number 25, that would be B. Every 12 minutes, bus A completes a trip from P to X to S to X to P. Every 20 minutes, bus P completes a trip from Q to X to T to X to Q. Every 28 minutes, bus C completes a trip from R to X to U to X to R. At 1 p.m., bus A, B, C depart PQR respectively, each driving at a constant speed and turning around instantly at the end point of its route. Each bus runs until 11 p.m. At how many times between 5 and 10 p.m. will 2 or more buses arrive at X at the same time? Well, we need to make a table. And let's first talk about this. So our starting point is 1 p.m. And that's where we have P. And then I'm just going to write the numbers, make it a little bit faster. So at exactly 3 minutes later, it'll be at X, then 3 minutes later at S, then 3 minutes later at X again, and then finally at 3 minutes later back at P. In 12 minutes, it makes that journey. And in a very similar way, if you keep going 15, 18, 21, and 24, it would again be X, S, X, P. So obviously, it's at X at these times. And as you can clearly see, it starts at 3, but every 6 minutes it's back at X. In a very similar way, we'll do the story for bus B. It starts at 1 p.m. and it is originally at Q. And then every, 20 minutes, so you got to divide that by 4. So every 5 minutes, so 5, 10, 15, and 20 is where it meets at X, T, X, and then back at Q again. And in a very similar way, every 5 minutes after that, 25, 30, 35, and 40, it would be at XT, XQ, XT, XQ, like that. So here, as you can clearly see, you start at 5 minutes, but then every 10 minutes after that, you're going to be back at X. Same story for C, slightly different numbers though. This time it's R, XU, XR. And then it's 28 minutes every 7 minutes. So 7, 14, 21, 28 is your R, XU, XR. And then 35, 42, 49, and 56. XU, XR. Like that. All right, so that means every 7 minutes, it starts at 7, but then every 14 minutes, it's going to be at X. All right, so we have covered that. Now, it starts at 1, and then we want between 5 and 10. So just be careful here. It starts at 1 p.m., and I'm going to convert everything to minutes to make it easier. 5 p.m. is 4 hours later. So write that here. 5 p.m. is 4 hours later. So 4 times 60 is 240 minutes. So this is where it begins in terms of where we want to look at when they meet. Between. And then 10 p.m., that compared to 1 p.m., is 9 hours later, right? And 9 hours is 9 times 60, which is 540. Like that. So we want to look at times in between 240 and 540. Okay. Well, at this point, you're just adding 6 every time. So if you just kept adding 6 to 21, or actually adding 6 to 3, really, that's the starting point. You eventually get to where we are. And the first time you get above 240 is 243. And then 249. You're just adding 6 every time. Dot, dot, dot. You just keep adding 6 every time. And then you eventually get to 537. That's the last time before 540, which represents our 10 p.m. So you can make a little formula. It's really 243 plus 6K. And that's a pretty straightforward formula. So same thing here. We want between 240 and 540 minutes. You're starting with 5 and you're adding 10 each time. So the first time you get above 245 is, the first time you get above 240 is 245. And then you're adding 10 each time, so 255, dot, dot, dot. And then eventually you get to 535, which is the last time before 540, which is 10 p.m. So this formula is 245 plus 10K, or 10M. Let's use different letters because it's not necessarily going to be the same value. Okay, by now I think you're an expert. This is 240. This is 540. You are starting at 7. You're adding 14 each time. And then when you keep doing that, eventually you get to 245 as the first time, and then 259 because you're adding 14 every time, and then dot, dot, dot. And then eventually you get to 539. So right before our 10 p.m. cutoff. And this one is what? 245 plus 14N. All right, so we have established that. So the question basically boils down to saying, when do we have 243 plus 6K, which is bus A, equal to bus B, which is 245 plus 10M? Also, the question is saying, when is bus B equal to bus C, which would be 245 plus 10M is equal to 245 plus 14N. And then one final comparison would be A equal to C, and that would be 243 plus 6K is equal to 245 plus 14N. All right, so let's do those three, and that should be sufficient to figure out our answer. All right, so here we go. The first one, this one right here, that one gives us, let's see here, 6K minus 10M is equal to 2. Divide through by 2, and I get 3K minus 5M is equal to 1. So now I'll make a little table, K and M, and try to get integer solutions. So start plugging away, and 2 and 1, that will work. 7 and 4, 12, and 7, and so on. You can pretty much get a very quick pattern. It looks like it goes up by 5, so 17, 22, 27, 32, 37, 42, 47. And then I'm going to put the time, because the time's important. So for example, when K is 2 and M is 1, when K is 2 and you plug it into there, you get 242 plus 12, which is 255. So I'm going to put the time here. Actually, it's not 255 in terms of the time, like 2 hours and 55 minutes. It's 255 minutes. So I just want to make that clarification. Okay, very similarly, you do the same thing, and you get 285, 315. These are minutes, of course, 345 minutes from this 1 p.m. Let's see here. That just got to make this match here. 375, 405, 435, 465. Are we adding 30 every time? Yeah, I could have just added 30 every time. 495 and then 525. Okay. So how many did I get? Because if I go another 30, I'll be at 555, and that goes above my boundary, which was 540. So I got to stop at 525. All right, so how many did I get here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 10 times that bus A meets bus B. So let's now go to bus C and B. So this gives me 245. Oh, those cancel. So it's just 10m is equal to 14n. Okay, and then I guess I can divide through by 2. 5m is equal to 7n. So again, make a little table, and off we go. So it looks like the first solution is 0 and 0. That's helpful. And then 7 and 5. And then I think just multiples. So 14 and 10, 21 and 15, 28 and 20. And then after that, I think it'll be above the 540. Let's just write out our times. This one is just 245. When m is 7, and we put in there, it's going to be 70 plus 245, which is 315. And then I think I'm adding 70 each time. So 385, 455, and then 525. And then that's basically at the cutoff, because the cutoff is 540. So here I got 5. But we got to eliminate doubles. That's the key to this question, in my opinion. 315 has already been counted, and so has 525. So 315 here, I cannot count again as a unique spot or time. So I only really have 3 new ones. So I got to put that here, only 3 new. So these 3 are the ones that I'm going to count in my cumulative total. All right, one last one. This one gives me 6k. Let's see here, 6k minus 14n is equal to 2. That means 3k minus 7n is equal to 1. All right, same thing here. We've got to make a little table, and off we go. So we get integer solutions as following. 5 and 2, 12 and 5, 19 and 8, and I think it goes up by 7 each time. So 26, 33, 40, 47. And I think after that we meet the cutoff. So the times, plugging back into here, for k is 5, it will be 243 plus 30, which is 273. And then same thing, 315, 357. It looks like I'm adding a certain, 42 I think I'm adding every time. Yeah, I think so. And then 399, 441, 483, and then 525. And then if I add another 42, I'll go over that 540 boundary. Okay, so I got 7 here, but again, 315 and 525 are already counted, so I only got 5 new. All right, so now I'm ready to add my total. 10, 3, and 5. So that is 18. So 18 times those buses will meet, and therefore number 25, the answer is A. Jonas has 1728 copies of a 1 by 1 by 1 cube with the net shown, where C is a positive integer and C is less than 100. Using these 1728 cubes, Jonas builds a large 12 by 12 by 12 cube in such a way that the sum of the numbers on the exterior faces is as large as possible. For some values of C, the sum of the numbers on the exterior faces is between 80,000 and 85,000. The number of such values of C is. Well, let's make a cube, and let's talk about this now. So this cube is going to serve as our diagram. Now, I'm going to draw a smaller cube, or not cube, but a smaller square inside of it. And I will illustrate a few things here. Now, when we are drawing these cubes, we have to understand that this is going to create the full shape. And there's a few types. The first is the corners, like that. That is one such shape. The second type are what I'm going to call sides, the ones that sort of come on the sides like that. That is a good example. And the third type of shape is just in the interior. We'll just call it in the middle. There's a lot of those. There's going to be a lot of those guys. So that is basically the three types. So we have either a middle, or we have a side, or we have a corner. And it won't take that much time to figure out each. So let's go through these. Each face of these cubes is a 12 by 12 face. The whole cube is 12 by 12 by 12, but each face is 12 by 12. So let's just write that. Each face is 12 by 12, which is 144. So there's going to be 144 of those small, squares on each face. But each face is broken up into middle, side, and corner, right? How many are in the middle, how many are on the side, and how many on the corner? Well, the middle, I think, is the easiest to figure out. We have one here and one here, so that makes this 10. Similarly, that makes this 10. So the middle is just a 10 by 10 square. So the middle is 10 by 10, which is 100. So there's 100 of those, 144, in the middle. Okay? Now the corner, well, the corners are easy, right? There's only 4 corners. There you go. You got one here, one there, and one there. So 4 corners on each face. So just put a 4 there. And then so far I had, of the 144, 100 allotted here, 4 allotted here. That leaves 40. I don't even need to count. I can just subtract it from 144. So 100 in the middle, 40 on the sides, and 4 in the corner. Okay. So now we're ready for the next step, which is to figure out the total. The total, of course, will be very similar. The only thing we have to do is multiply by 6 because there's 6 faces. We did this for each face, but there's 6 faces to a cube. So middle, it would be 6 times 100. And that's 600, of course. And then we have to get the maximum sum. The sum on the exterior, the numbers have to be as large as possible. Well, the ones in the middle, they only take up one of these, correct? Only one of those will show on the exterior. The other ones will be buried inside the cube. And of these, the maximum is 100. Why? Because C is less than 100. So each of those will have 100 if I choose 100 as the face being shown on the exterior. So that will give me 6 times 100 times 100, which is 60,000. So 60,000 will come from those guys. That's the maximum I can make it, the ones in the middle. Same philosophy for the side. I've got to multiply the total by 6 because there's 6 faces, 40. But here's the thing. On the side, 2. You notice? 1 and 2. 2 faces show from this. Okay. From one of those, first let's just figure out what this is. This is 240, right? Okay. We got to break that up into 2. Half and half, right? Because each of those sides will have 2 faces. For one of them, I will choose the 100. So then I multiply that by 100, and I get 12,000. But then for the other one, I can't choose 100 again. I've got to choose one of these C's. So I'll multiply that by C, and I get 120C. So that's about all I can do there. That's the maximum I can make it. Now the corners. First, we got to multiply it by 6. Gives me 24. Correct? But the corners, there's 3 faces showing. 1, 2, 3. Okay? So the 24, I got to break it up into 8, 8, and 8. Right? Because I've got to look at it from the perspective of those 24 have to be divided into 3 sections. The first section, I will put 100 as the max. So I can multiply that by 100. That's 800. The next one, if 100 is allotted, then the other ones have to be C's. So this one I have to multiply by C, and this one I got to multiply by C. So that's 8C, and that's 8C. And that's it. That's pretty much the total. So now let's add it all up. What is the total? It's this, plus this, plus this, plus this, plus this, plus this. Okay? So that is, let's see here, in terms of numbers, 72,000 and then 800, right? So 72,800. And in terms of the C's, it looks like 120 and 8 and 8. So that's 120 plus 16. So 136C. Yeah. And they're saying that's between 80,000 and 85,000. Okay? So it's between 85,000 and 80,000. Okay, I think that's a fairly straightforward inequality to solve. So here we go. First thing is bring the 72,800 to one side. And if I subtract it from both sides, I'll get 200 on that side and 7,200 on one side. And then divide through by 136, and that brings me to just C in the middle. This side will be 89.7 approximately. And on this side, it'll be 52.9, approximately. Well, C is an integer, right? Yeah, C is a positive integer. So because C is a positive integer, I can't use these decimals, so I've got to use the integers. If C is less than 89.7, then that means it must be less than or equal to 89, because that's the first integer below 89.7. Similarly, if it's greater than 52.9, it's got to be less than or equal to 53. So there you go. C is any integer between 53 and 89 inclusive. So that means the number of values for C are 89 minus 52, right? You're counting all the integers from 53 to 89 inclusive, and 89 minus 52 is 37. And there you go. 37 is the answer to number 25, and that would be C.